Alrighty, guys. So I'm still going to do some more substitution examples in this video. So we did all this one in the last video, and what I did was I wrote down 3 examples on 71 to try. Okay, so when we were talking about substitution, what I'm looking for, hopefully, is one equation set equal to a letter. Unfortunately, in this one, I don't have that. Or I'm kind of looking for both the equations to be equal to a letter, and I definitely don't have that. So this is kind of like the second scenario where no equation is set equal to a variable. So we need to get a letter alone first, and I look for a letter without a number. So if I look at these 2 equations right here, this one is the best one to solve for, x right there, because that is a letter without a number. So to solve for it, I would subtract the 3y on both sides and then have the equation x equals negative 3y plus 3. And now that I have one equation set equal to a letter, I can put this in for that letter in the other equation. So when we take this top equation now and I rewrite it, in place of x, I'm going to put this negative 3y plus 3 plus 3y equals 6, finish out the equation. Then I can solve because I only have the letter y, and so I'll distribute, and we'll have negative 6y plus 6 plus 3y equals 6. Then I'm going to want to combine like terms, and negative 6y positive 3y is negative 3y plus 6 equals 6. Then I can subtract 6 on both sides to get y all by itself, and we'll have negative 3y equals 0. And then I'll divide by negative 3 on both sides, and y is 0. But I also got to solve for x, so if I take this guy and plug it in for y in this solved for x already equation, we'll have negative 3 times 0 plus 3. And so I get that x equals 0 plus 3, which is 3. So these 2 lines cross at the point 3, 0. Okay, on to example 2. In example 2, both these equations are set equal to y. So that's like this last option here. Both equations are set equal to a variable. So this is kind of like what I like to call left to right substitution. So like I'm just putting these 2 equations on the left and then on the right. So we'll just have 3x minus 2 equals 1/3 x plus 2. And I know it's scary because it's a fraction, but you can do it. We can do it. So I'm going to want to get my x's on the same side. The 1/3 is smaller, so I'm going to subtract it. And if I have 3 wholes and I take away a third, not of the total, but a third off of one of them, I think I have 2 wholes left and then 2/3. That's 0, and this is 2. Then I can add the 2 over, and so we'll have, actually I hate to have a mixed number like that, so the way you make a mixed number into an improper fraction is we multiply then add. So 6, 7, 8 over 3x equals 4. And then to get rid of a fraction that's on x, I need to multiply by the reciprocal, so 3 over 8 on both sides. And that 4 is really over 1, and the reason I like to do that is because now I can see that I can cross cancel and get a 2 down here, because like 4 goes into itself 1 time and into 8 2 times. And so we have 3 over 2, or 1 0.5. And now I know x. So if I want to solve for y, you can plug it into either one. And I know you probably want to avoid the fraction, but I'm actually going to pick the one with the fraction because I love them so much, but also because we're going to take that 1/3 and then in place of x, I'm going to put the 3/2. And I saw that there would be a 3 on top and a 3 on bottom. So I can cross cancel, which is so nice. So like the 3's will divide out. And we're just left with 1/2 or half plus 2, which half plus 2 is 2.5, or like 5/2. Like if we're going to be in fraction land, we might as well just be there. And so these two lines do cross each other at not a very nice spot, 3/2, 5/2, which actually both these equations I picked from our graphing examples before. So like this first one, this 2x plus 3y equals 6 one, that was this one here. And we can see graphically, they do cross at 3, 0. And I can find that algebraically as well. This one was this first equation where they crossed at not a very nice spot. And so I kind of had to guess that they were going to cross at like 1.5-ish, 2.5-ish. But now that I've solved it algebraically, I know for a fact that it is exactly at 1.5 and 2.5. This was a little bit of a guess because I can't be a perfect grapher. Like we're going to try, but the lines aren't always super straight. This is algebraic, so I know it's correct. Last one to try. On this last one, I do already have a letter solved for, so that y is already by itself. So in place of y in my second equation, I can plug it in. So I have 3x minus 2, and then in place of y, we'll put 3/2x minus 1 equals 2. And then I can solve because I only have one letter, but I got to distribute. So we'll have 3x. Now, when I do this 2 times this 3/2, the 2's will divide out because one's on top, one's on bottom. And we'll just have negative 3x. And then negative 2 times a negative 1 is a positive 2. Oh. 3x minus 3x is 0. And I have 2 equals 2. And I don't have any more x to solve for. So when that happens, when your x disappears, that means you either have no solution or infinite solution. So really different answers. Either you have none or you have all of them. And the way you can tell is if this statement right here makes sense or doesn't make sense. Now, 2 does equal 2. So this does have lots of solutions. Actually, infinite. So this has infinite solutions. Which, again, these 2 equations were some of our lines from before. Like back here. This line, y equals 2/3 x minus 1, and that line were right on top of each other. So they had infinite solutions. So that's how it shows up algebraically. All the x's disappear and you have a true statement. So hopefully that helps us a little bit more with substitution. Yeah, I'll see you next time.